So what happens if the function, your integrand, has a branch cut? Well, you're not allowed to integrate through a branch cut ever. You're not allowed to, wherever you integrate, must be smooth. But actually a branch cut can be remarkably helpful, because what you can do is choose a contour which basically hugs the branch cut. It goes around the branch cut. So okay, we integrate along the branch cut. There's your branch point. But you see, if you integrate along here and do something like this, integrate back the other way, then these two contributions to your contour integral will not cancel out, because the function here, the function at this point here, has a different value from the function at that point. That's the whole idea of a branch cut. There's a sudden jump in the value. So in general, the integral along here would be different from the integral along here. So they don't cancel out. And if you're lucky, then the integral along here will just be a multiple of the integral you want. So normally the integral you want is along here, and this will just be a multiple of the integral you want, which is not minus 1 times the integral you want. Okay, so the typical branch, a typical contour looks something like this. There's a circle around here which comes back and joins up like this. Life is often easier if it's possible to relocate the branch point to 0. So people normally do that just with a change of variables, in which case you get this situation here. You've got a branch cut, and okay, most of the time you're integrating from 0 to infinity, so you actually want the branch cut along the real axis. So you can have this situation, and then we integrate around here and do a circular integral around here, and this is radius r. So, and then what you would hope is that this integral around here would tend to 0 as r goes to infinity. The thing you have to be careful about now is what happens here. Just be aware that a branch point and a singularity are two different things. At a branch point, the function might well not have normally does not have a pole. So, but basically what happens here is you do have to be careful. I mean, what we're going to consider is that this distance here, we now actually have two limits to consider. So we consider the limit as both r goes to infinity and also as epsilon goes to 0. And as well as considering this integral around here as r goes to infinity, we also need to consider this semicircular integral very close to the branch point. Normally this tends to 0, but we need to check that. Sometimes it tends to a finite value, that's also okay, but we always need to check what the limit of this integral is as epsilon goes to 0. So this is one possibility. Another possibility, which if you can do it, if it's possible to solve the problem this way, is a little less work, and that is to do this, where we just do a semicircle going around like this, and then we integrate back along the negative real axis. So whether you can do this or not, whether you can get away with just this contour or you need to use the whole circle, depends on the problem, as we'll see with examples. The advantage, of course, of using this is that if you've got poles above and below the real axis, then obviously in this case you only need to evaluate the residues at these poles, not both. So if you can use a semicircular contour, then that saves you a bit of work.